Hello everyone. This is a video presentation I made about my paper Improving Delay and Capacity of TS-LoRa with Flexible GuardTimes. First of all, I will say a few words about LoRa and LoRaWAN for those who are not familiar with the topic. So LoRa is a proprietary spectrum modulation whose main characteristic is that it rates data rate with sensitivity. This means that the lower the bit rate, the better the sensitivity, and thus the longer the transmission range. To control the amount of spread, LoRa uses 6 spreading factors from 7 to 12. The higher the spreading factor, the lower the data rate and the longer the range. But this also means that the transmission time and the energy consumption increase with higher spreading factors. On the other hand, LoRaWAN is an open source protocol proposed by the LoRa Alliance and makes use of the LoRa physical layer. It adopts a pure Aloha MAC, which means that collisions may happen. And as a consequence, it does not have any performance guarantees. So the question that someone can ask is, can we use time-slotted, collision-free maybe LoRa communication to provide performance guarantees such as fixed delay and high packet delivery ratio? The answer is yes, and thanks to the long-range characteristics of the LoRa, we can achieve many things like reduce the cost by eliminating intermediate nodes, so no need to have routing unless we want very, very long ranges. And we can also enhance mobility. We can use such a protocol in industrial and home automation, and actually in every application that requires frequent packet rates and reliable communications. Of course, as with all time-slotted protocols, there are some implications. Switching from an Aloha-based approach to a time-slotted one, we cannot have infinite capacity nor variable packet sizes. So in order to achieve the delay requirements we want, the capacity must be fixed. Or we must have a trade-off between capacity and delay. Another requirement is that clock synchronization must be achieved, so the nodes have to periodically wake up to receive some synchronization data from the gateway. Another important factor is the scheduling of transmissions. We have to find a way to put the transmission in order and let the nodes know about this order, which actually in LoRa networks it's not trivial because of the duty cycle restrictions and the low data rates. So for these reasons, we have proposed TS-LoRa. TS-LoRa is a collision-free time-slotted protocol that uses an autonomous slot assignment mechanism during the over-the-air activation of the joining node. This is equivalent of the OTAA registration mechanism of LoRaWAN for those who are familiar with LoRaWAN. So during this registration, the nodes send some information like the device EUI, something like MAC address, along with some other fields, and it gets back along with some other fields the device address. So in TS-LoRa we manipulate this device address, and using a simple hash function we translate this device address to slot number. So using the same registration mechanism as LoRaWAN, we can get the slot without transmitting extra information. If you want to know more about this mechanism, you can check the publication on the bottom of this slide. TS-LoRa uses multiple parallel frames, one for each spreading factor. For example, in this figure, we have two frame structures, one for spreading factor 7 and one for spreading factor 8. Each spreading factor frame contains a number of slots. In this particular example, we have node A and B accommodated in spreading factor 7 frame, and node C accommodated in spreading factor 8 frame. And these frames are repeated over time. In the end of the frame, we have a downlink slot for synchronization and acknowledgements that is called SAC, as you can see here. Each spreading factor frame has its own SAC slot. A spreading factor frame has a minimum length as it is dictated by the duty cycle regulations. And finally, GuardTimes are added in between successive transmissions, here for example, or here, so that they tolerate slight desynchronizations. So currently TS-LoRa uses fixed GuardTimes. This means that all slots have two equal GuardTimes, one before and one after its transmission, as we can see here with this dark area. The size of the GuardTime is decided based on the time passed since the last synchronization, since the last received SAC packet of the last slot, slot N in this case. But actually someone could ask why the previous slot should have the first slots, for example slot 1, should have the same GuardTime as the slot N, because the first slot we will have it here again. So why this GuardTime should be very long as this GuardTime, for example? So this is the question. This is a reasonable question. So I came up with a solution, and I said, why not using flexible GuardTimes? So actually the contribution of the paper is that we introduce flexible GuardTimes where we assess the possibility of using those GuardTimes to increase capacity. In this case, the GuardTimes increase as we move to higher slot numbers. So as you can see here, the GuardTime of the first slot is tiny compared to the GuardTime of the 9th slot. In this way, we can save some of the time that otherwise would be used for GuardTimes, and thus accommodate more slots and increase capacity. You can see here the comparison between the fixed GuardTimes here and the flexible GuardTimes here. You can see that we save this amount of time in this particular figure, for example. So imagine if we have at least 100 slots, how much time we can save. So using mathematical analysis, which is presented in the paper in detail, we can observe a capacity increase of up to 29%, especially for the lower spreading factors, for example here or here. Of course, this advantage diminishes as we move to higher spreading factors due to the lower number of nodes that we can accommodate in those spreading factor frames. For example, here we have much less number of nodes than what we have in a spreading factor 7 frame. A number of experiments were also conducted to assess the transmission overlaps in successive slots. Actually, the purpose of the experiments was not to assess the capacity, because this would require at least 100 nodes and considerable financial and manpower resources. So in this particular experiment, we used 8 PICOM low pi 4 nodes transmitting 1000 packets each. We experimented with spreading factor 7 and a single channel with 125 kilohertz width. Also, the packet size was set to 16 bytes and the transmission rate was about 6 seconds. So this was actually the 6-second delay constraint that we had, that actually was dictated by the duty cycle rules 1%. The results, as you can see, reveal very high packet delivery ratios, actually exceed 99.9% most of the time. And even though some slots present higher number of retransmissions, as we can see here, the flexible GuardTimes scheme seems that works. Actually, I discovered that these retransmissions here were mainly due to a bug, PICOM bug, that was bypassed in the newer versions of the TS-LoRa code. Part of the future work is to measure in detail gaps or overlaps between successive slots, successive transmissions. To do so, special hardware like power analyzers are required, so we have to wait a bit to return to the labs to do all those experiments. Also, another thing we want to assess is to use flexible GuardTimes with high spreading factors and see what happens there. And also experiment under different environmental conditions, because as we know, the crystal sensitivity that actually drive the clock are affected by the temperature. Thank you for watching this video, and I would be happy to answer any questions.